Hello everyone and welcome to the second lecture of Positional Astronomy, which was started by which, the series which was started by GRAMOLY. And in the previous lecture, we learned the equatorial coordinate system and the horizontal coordinate system and the rest of the basic terms in the uh, coordinate systems. And in this video, we'll be learning spherical trigonometry and the conversion between various coordinate systems. Not like various, just between like the equatorial and horizontal coordinate system and the ecliptic and equatorial coordinate system. And as an exercise, you're going to be deriving the equations for conversion from the ecliptic to horizontal coordinate system after watching this video, of course. Now, before starting, I'd just like to address a few points. Firstly, that if you require any kind of help with the questions or anything which I provide at the end of the lecture, you can just ping me on the server or just ping a volunteer on the server, the GRAMOLY server, of course, and they would be happy enough to help you out. And the second thing is that if you're having any issues with these videos, or if you see any uh, aperture of improvement, then you can just write down in the comments below or DM me on Discord or just ping me on the server. I think in for the last video, some people were saying that my audio was low, and I hope now it's fine. Okay, so now that I have addressed these points, let's just. Okay, so we start by deriving the formulas um, for the spherical circle. So we first drew the circle or on this paper as our sphere, and we drew 3 points and connected them with these arcs A, B, and C. Okay, now we drew two tangents from A, one of them which would be tangent to the great circle passing through AC. I have defined the great circle in the previous lecture. Okay, and one tangent would pass with the great circle passing through AB. Now, as you have studied, the angle between these tangents, okay, let's just say this is this other tangent. So the angle between these tangents, theta, would be the angle between these great circles at the intersection. All right, so A is the intersection, if you can assume. Then the angle, the spherical angle to be precise, the spherical angle CAB would be equal to this angle, which is BAE. Okay, so as I have written here, from the figure, spherical angle BAC is defined to be the angle between tangents at A to great circles AB and AC. So BAC is equal to DAE. So BAC, we can just write it as A for our convenience. Okay, just for simplicity, as it is opposite to arc A, and similarly this angle is angle C, this is angle B. Okay, let's just move to the next page. Let me just copy this. Now we define angle EOA. Okay, EOA to be equal to B. Okay, this angle is the angle of arc B, of course, and this angle is the angle of arc C, and this angle basically DOE or BOC is the angle of arc A, because this OE is just an extension and OB is an extension of OB. So BOE is equal to BOC. And so we have defined EOA to be B and EOA to be B and DOA to be C. Now we can write that AD, thus AD be equal to tan C. And another thing which I'd want to point out is that I've defined OA to be 1. That is, I'm using a unit sphere. But if you don't use a unit sphere, yeah, as I have written here, but if you don't use a unit sphere, you would still end up with the same results. So it's really nothing to worry about. So I wrote OD as secant of C. Okay. And similarly, you can write AE as tangent of B, and OE as secant of B. Now, from the law of cosines in Euclidean geometry, you can write AE square plus AD square minus 2 AEAD is equal to DE square. I hope you are familiar with the law of cosines. It's taught in vectors. Okay, and similarly, you can write that cosine of angle A. Okay, this angle A, which is here, capital A, and similarly, you can write DE squared to be equal to OE squared plus OD squared minus 2 ODOE times angle small a, or the angle of arc A, as I have probably described this before a few minutes back. Okay, since they are equal, you just equate them and you get tangent squared C plus tangent squared B is 2 tan C tan B. Cosine of capital A is secant square C plus secant square B minus 2 secant C secant B cosine of A. And just solve this. Okay, solve this and you would end up with cosine of small a is equal to cosine of B times cosine of C plus sine of B times sine of C times cosine of capital A, which is the spherical angle opposite to arc A. Okay, this is really important because it's like the basic thing. Really important. As I've written here, this is the law of cosine for spherical triangles, or the cosine rule. I think it is more commonly called as cosine rule, whatever. Now let's move to deriving the sine rule. Let me just paste. Okay, let me just go back and paste this here. I'll just delete it in a bit. So as you saw, cosine, you write sine of B times sine of C times cosine of spherical angle A. Just take it to the RHS and then you square it. It's deleted since you've seen this now. Okay, probably have learned this by now. Now when you square it, right, you get this. I'm not gonna read that, of course. You get this, and then you use the identity sine squared theta plus cos squared theta is 1, and then you get to this step, and now you rearrange the terms and you get the RHS as this 1 minus cosine squared A minus cosine squared B minus cosine squared C plus 2 cosine of A times cosine of B times cosine of C. Now, as you can observe, this is a cyclic sum, so it wouldn't depend on the LHS. So you just equate the possible combinations. Of course, these three angles need to be different. So you get sine of sine squared b, sine squared c, times sine squared spherical angle a, and then you equate it with sine squared a, sine squared b, sine squared spherical angle c, equated with sine squared a, sine squared c, sine squared spherical angle b. So you cancel the stuff, take the square root, and you end up with the sine rule for spherical triangle. And if you observe, just tend r to 0, not really 0, sorry, just tend arcs to 0, and you'd observe that this is similar to the sine rule for a triangle. Okay. Yeah. Now let's move to the next section, which is the conversion of. Before moving to the next section, I'm just gonna give you two exercise. So you should prove the analog of the cosine rule in spherical triangle, and it states that sine of A times cosine of spherical angle B is equal to cosine of B cosine of C minus cosine of C sine of B times cosine of spherical angle A. Sorry, this should be sine of C here. Just here, sine of C. Alright, and then you have to prove this formula, which says that cosine of A times cosine of spherical angle C is equal to sine of A times cot B minus sine of C times cot of spherical angle B. This is the 4 parts formula, and this is the analog of the cosine rule. It is recommended that you learn these two as well, but it is compulsory that you learn the cosine rule and the sine rule. This is just as a summary. You can pause and learn this. And another exercise which I would like to add, right up here, we derive previous section on your own. Basically, the sine rule and the cosine rule, derive it on your own, as I think you would be familiar with the derivation. So just pause the video and derive it, and when you are comfortable, you can skip to the next section. Okay, so this is the next section of coordinates transformation, and we are going to be starting with between the horizontal and equator to the coordinate systems. First, this is the superposition of the equatorial coordinate system onto the horizontal coordinate system, which is, if I can elaborate a bit on this, more on this, this was your Earth, but I think you guys should be familiar with this, as I drew this diagram a couple of times in the previous lecture, but still, for the sake of explaining, I'm just going to draw it again. Why not? Okay, so this was your zenith, this was your NCP, and this was your latitude, this was by North Pole, this is the South Pole, and this is the celestial equator. See, this is the declination of a star. So this diagram, this diagram is just basically the superposition of the equatorial system to the horizontal coordinate system. That's it. So this is the equator onto the projected onto the system. So suppose you have a star X, whose declination is delta and whose altitude is A, and this is the latitude as I described it. This angle is the R angle of the star. I think I described the R angle too in the previous lecture, but if you don't remember, R angle is just the time passed from the culmination of the star, and culmination is when the star is on the meridian of the person, so which means the star is just on the meridian of the northern direction and the sun in this meridian. So this is just the D or the R angle. Now suppose the right ascension of this star is alpha. Just put this 2 here. And suppose this is alpha. So as you can see, sorry, the the sidereal time is just the time from the uh, first point of Aries, which is the right ascension 0 point. So you can write the spherical time. Sorry, why am I saying spherical again? Sorry, it's the sidereal time. It's just equal to the R angle plus the alpha, which is the right ascension. So if you are given the sidereal time and the right ascension, you can easily calculate the R angle too. So it's just the addition, which I didn't do in the diagram. Well, let's just remove this. And move on to some markings and stuff. So as you can see, the arc XC represents the angle A or the angle of the altitude, and the arc XP is the angle of declination, NP is just latitude, XC is 90, so just the complementary angles. The XC is 90 minus A, XP is 90 minus delta, and PZ is 90 minus phi. And this ZPX is the 360 minus the azimuth, because as I told you in the previous lecture, the azimuth is measured from the clockwise direction from north. If you're saying this from the top, so it should be 360 minus A PZX. Okay, this angle PZX, and ZPX is just the R angle T or H, however you want to represent it. Now let's move on to the next, not really next section, but the next page, where we'll derive the equations. All right. let's just paste these equations if you have still not learned it for your convenience. We are only going to be needing these two for now. Right. So you can use the cosine rule on angle the arc zx, and you can write this. Yep. You can write cosine of zx. Cosine of zx is equal to cosine of pz times cosine of px plus sine of pz times sine of px times the cosine of spherical angle opposite to zx, which is just the r angle, and you get sine of the altitude is equal to sine of the latitude times sine of declination plus sine of latitude, sorry, plus cosine of latitude times cosine of declination times cosine of the r angle. So you have just converted from the equatorial system to the horizontal system. And you have declination and latitude here, and you have the altitude here. Now, one application of this formula, I don't think you should really learn this. You can always derive this in the exam, and moreover, it's not gonna come in AOQA part 1, hopefully, and not even part 2. I haven't seen such any questions come in the part 2 as of now, but yeah, there are many applications of spherical trigonometry, as I was saying that in the last year we had the calculation of early sunrise and sunsets on different locations of the. I think this was the last question on the IOK part 2, and you can also solve this using this formula. Okay, and as I was saying, I don't think you should learn this and have quite a lot of time in the Olympiads, and this will take like 2 minutes or so to derive on your phone. Okay, but it is although recommended that we learn. So one of the applications, returning back to the topic, of course, one of the applications which I was talking about was the calculation of sunrise or sunset. Of course, you know at the sunrise or sunset, the altitude is 0. So if you just substitute A to be 0, you just take it to the RHS and then divide it by the cosine of phi, cosine of tan delta. You get the relation between phi and delta and the R angle. So suppose you want to calculate the day, duration of day at a particular declination of the sun, that is on a particular day and at a particular location, you can calculate easily with this formula. And as I have given, you'll come to know what uh, the exercise which I've given at the last page or at the end of the lecture. Now, using the sine rule here, you can write the sine of arc zx over sine of the r angle is equal to sine of arc px over sine of 360 minus azimuth, and this gives you just negative sine of the azimuth times cosine of altitude is cosine of declination times sine of the r angle, and that's it. These two formulas. Although if you want, and I think I should probably give this as an exercise for you. Yeah, too many exercises, isn't it? Okay, so now getting back to the topic, what I want is that you should derive one more relation using the 4 parts formula or the n log of the cosine rule. One more relation between the coordinates of the equatorial system and the horizontal system, just for the sake of practice. Of course, this requires a lot of practice to master. So what I want is that you should again derive these on your own, as I told you for the first section of spherical trigonometry. Right? It is very important that you learn the cosine and sine and how you have to approach the derivation of the equations of conversions. Now, moving on to the next section, we have the not really next section, but the conversion between the horizontal and equatorial system. This is just Control C, Control V from the previous section. Just you have px in here as because you want to find declination instead of zx, and because you wanted to find altitude in that case, and in this case you have to find the declination as it is horizontal to equatorial. So yeah, you use the cosine rule again. I'm not gonna explain this, just look at this. Using the sine rule, you obviously get the same result as the previous result. Now let's move on to the next section, which is hopefully the conversion of conversion from ecliptic to equatorial and vice versa. Yeah. Now let's discuss these terms a bit. Firstly, let me just zoom in a bit so it's clear. This is the RA equal to 0 meridian. R equal to 0. This is R equal to alpha. O is any star which you are observing. Of course, this is the first point of Aries. And as I said, the ecliptic is just tilted 23.5 degrees from the equatorial plane. You draw a great circle tilted 23.5 degrees with the equator. And just like we have the right ascension here and the declination in the equatorial system, as a direct consequence of that, not really consequence, but as a similarity, we have lambda. So from alpha we have lambda in the ecliptic system, and from delta we have beta. Okay, as you can see, the ecliptic longitude is lambda here and the ecliptic latitude is beta. This is the north ecliptic pole and this is the north celestial pole, and of course they are tilted by an angle of and of course they are north ecliptic pole is tilted by an angle of epsilon, which is equal to the angle of tilt of earth, which is 23.5 degrees. Now let's talk about some angles, shall we? The angle NE, NC and X is just 90, which is this angle, plus alpha, which is this angle. So 90 plus alpha is angle NE, or precisely spherical angle NENCX, and the angle NENCY, sorry, NCNEY is just the 90, which is this angle, 90 minus lambda. As you can see, this is 90. This first point of Aries. This is lambda. So we subtracted this and we get 90 minus lambda. All right. Now we can write the arc NCO to be 90 minus delta, of course, as arc OX is delta, and the arc NEO to be 90 minus beta, as arc OB is beta, of course. Now what I want you is pause the video and derive the relations between beta and delta on your own, and after you have done, uh, just unpause and watch the derivations to know if you are correct. I hope you have paused. Yep, moving to the next page. All right. So we use cosine rule. Since we are converting equatorial to ecliptic, we need to find beta. So we use the cosine rule here. Cos of NEO is cos of epsilon times cos of this angle NCO plus sine of epsilon times sine of NCO, which is 90 minus delta, times cosine of the angle opposite to NEO, which is 90 plus alpha. Right, and then you just do the simplifications and you get this relation: sine of beta is equal to cosine of epsilon sine of delta minus sine of epsilon cosine of delta sine of alpha. And now of course you use the sine rule and you get sine of n c and e and y, which is the sine of 90 minus lambda over the arc opposite to it, which is the sine of NCO, which is the sine of 90 minus theta, and we use the sine of NC, NENCX, NENC and X, which is the sine of 90 plus alpha over the sine of NEO, which is 90 minus beta. You get cosine of alpha times cosine of delta is equal to cosine of lambda times cosine of beta. These are the two equations from the equatorial to ecliptic. Once again, if you want to learn it, you can, but what I do personally is that I derive them on the spot, because of course it doesn't require much work, and learning them is like a bit hard for me. Yeah, I'm bad at IOC. Alright, now of course we are going to be converting to ecliptic to equatorial too, and I'm not gonna really explain these as I have probably done this around 3 times. Okay, you just use the cosine rule here again for the arc NCO and you will get this, and of course the second rule, and sorry, the second equation you get is from the sine. One interesting application of this is this equation is that you can calculate the declination of a sun at a given point in time. All right, because you know that the beta of sun is always 0, as the ecliptic is path traced by the sun throughout the year. So you can write the sine of delta is equal to sine of epsilon times sine of lambda, and lambda, which you can calculate easily. And about the lambda and alpha things, we are going to be learning this in timekeeping systems, which is going to be a different series, but if only if this gets enough response, and only if you guys are really interested in continuing the astronomy lecture series, then we'll start with a timekeeping series. Why not? Although I think that was only the lecture, but still. Yeah, so at the concluding this lecture, I am giving three exercises. First is calculate the length of day on equinox and solstice on your location. Okay, on winter and summer solstice both. And second is calculate the time after winter solstice such that the sun is overhead or at your location. Right. If you want hints, as I said during the start of the lecture, just ping me or volunteer on the server. The third is find the zenith distance of Alpha Leo in Moscow for moment of sidereal time, 5 or 23.8 minutes. So yeah, that this is it about this lecture, and in the next lecture we are going to conclude this series by uh, just doing some problems from various competitions like the NAO, the INAO, although I don't think there's much of spherical trigonometry in the INAO, whatever, and the IAA, IOAA, and the IAO, and etc. etc. All right, thanks for watching, guys.